Hello, students. Very good morning. So, in this video, we are going to discuss about the topic, the time-dependent Schrodinger wave equation. Actually, the wave equations of motion for a wave function psi of s comma t, which was formulated by the Erwin Schrodinger during the year of the 1926. So this Schrodinger equation is a fundamental equation in quantum mechanics, as like the Newton's equations of motion in classical physics. So now, here, we are going to derive the one-dimensional equation for a free particle. Okay. So one-dimensional Schrodinger wave equation, time-dependent Schrodinger wave equation for a free particle that we are going to see. Okay, so let me discuss one by one with you. So please consider the wave equation. You need to consider the wave equation of a localized free particle. Okay, which is given in this equation where, okay, you can take this phase velocity that is equivalent to omega by k. You know, this phase velocity is related to the omega by k. And the same we can write in terms of the E by P. Right. So if you want to make the same in other form, means E is nothing but that is equivalent to mc square, and the momentum that is nothing mv. And from this, after this cancellation, m, so finally you will get c squared by p. So from this we can say the phase velocity equation is omega by k or E by P or C square by V. So now we need to think about the another one equation for the energy and related formula energy and momentum. Means please consider the, for a, please think for a free particle, right, for a free particle, the classical expression for energy, that is what? For free particle, the classical expression is nothing but energy is nothing but E is equivalent to P squared by 2m. This is general one. This we derived classically. Okay, energy is equivalent to P squared by 2m. Now here we need to replace the momentum. Actually, here we are talking about one dimension, so we can put Px. Take this equation now as a first. Energy is equivalent to Px squared by 2m. Here, you need to replace the momentum Px by k h cross. How? How the momentum P is equivalent to the k h cross? Because you have a formula, no? The momentum is nothing but h by lambda as per the de Broglie equation. So now you take h by lambda and multiply the 2 pi divided by the 2 pi. Take these two, h by 2 pi and 2 pi by lambda. That becomes what? H by 2 pi is h cross. Lambda by 2 pi, the 2 pi by lambda is a k. So momentum is nothing but h cross k or k h cross, whatever it is. And then here the energy, momentum, you should replace this formula k h cross. Like that, you please think about the energy that can be replaced by the h cross omega. How energy related to the H cross omega? Because E is equivalent to E is equivalent to H mu. Right. This is wrong. Take it. E is equivalent to H nu. So from this, we can use H. You know, omega is equal to 2 pi nu, na? Upon nu is equal to omega by 2 pi. So we can say this one H cross omega. So now you need to substitute this energy factor and the momentum factor, both you need to substitute in the equation number 1. So if you substitute, what you will get? H cross omega, that should be equivalent to the k square H cross square by 2m. So from H cross, 1 H cross cancel. So from this, omega is equivalent to H cross k square by 2m. This is equation number. So now take this omega, substituting this value omega in the equation, wave function equation. What is that? So wave function equation psi of x comma t, that is nothing, integral over minus infinity to plus infinity a of k exponential of I ks minus omega t, okay, kx minus omega t into dk. So now you need to substitute this omega value in this equation. So this equation becomes psi of x comma t is equivalent to integral over minus infinity to plus infinity a of k exponential of, keep I as such, then kx minus, instead of this omega, you substitute what? H cross k square by 2m into t into dk. Take this equation number 3. So now you need to differentiate this equation psi with respect to t first. So differentiate this equation differentiate the psi of x comma t with respect to time t. So what you will get? Take it. So dou psi by dou t, that is nothing. If you differentiate it, here with respect to time only we need to differentiate. So automatically what we will get after the differentiation, here this factor only the variable, this automatically will be the constant. No? So this only differentiable one, and based on that, please integrate this with respect to t now. If you integrate it, what you will get? Minus I h cross by 2m, and k square is also there, k square, then integral over minus infinity to plus infinity a of k exponential, the full term, same term, kx minus h cross k square by 2m t dk. This is equation number 4. Now, again, you need to differentiate the same equation with respect to x. Now, second term, differentiate the equation psi of x comma t with respect to x. So, with respect to x, if you will do, what you will get here? Dou psi by dou x. That is nothing. Actually here this complete term becomes 0 because there is no x component. So finally what you will get, ik integral over minus infinity to plus infinity a of k exponential I kx minus h cross k square by 2m into t into dk. Right. So now you please make some simplification. For further simplification, here you need to make the further differentiation with respect to x, second order. Again, you differentiate it. What you will get dou square psi by dou x square is equivalent to. Again, if you differentiate, again one more ik will come out. So I into I minus 1. So minus k square integral over minus infinity to plus infinity a of k exponential of I kx minus h cross k square by 2m into t into dk. Consider that this equation number 5. Now you need to combine the equation. Combine the equation 4 and 5. And if you compare it, you see in this equation 4 and 5. In this equation, these complete steps all there in the equation number 4 except I h cross by 2m. So take minus k square and the full of integral term. Here we have minus k square and full of this integral term. So, and this minus k square integral term becomes this dou square psi by dou x square. So, based on the comparison, we can write that dou psi by dou t that can be equivalent to I h cross by 2m dou square psi by dou x square. So now here you need to multiply I h cross on both sides. Right. So if you multiply it, what you will get I h cross dou psi by dou t is equivalent to minus h cross square by 2m dou square psi by dou x square. This is equation number 6. And this equation is one-dimensional Schrodinger equation for a free particle. Right. Now here we need to think one more point in the same equation, and we need to identify the momentum and the energy operator in the equation number 6. So I'm going to rewrite the same equation in another aspect. How? You please see my writing here. I h cross dou by dou t into psi of x comma t. That is okay. This is equivalent to, and here you please take the 1 by 2m separately, and remaining steps minus I h cross dou by dou x. Take it separately as again minus I h cross dou by dou x. Then psi of x comma t. So the above sixth equation can be rewritten as like this. And here you see this term I h cross dou by dou t, that is nothing, it is energy operator. And this term, that is nothing, it is equivalent to momentum operator minus I h cross dou by dou x. Okay, so additionally I am giving this one. Right, actually the equation number 6 is the equation, Schrodinger wave equation, one-dimensional Schrodinger equation, that is okay. So I am explaining in additionally this one. Here from this we can say the basic, what we derived the first equation is equal, what we started from the first equation. Energy is equivalent to p square by 2m. No, see this is p and this is p by 2m. So means this equation number 6 is nothing, it is general energy equation is equal to p square by 2m. In quantum mechanically, we derived this one in this form, in one dimensional. So now we are going to think about the three-dimensional Schrodinger wave equation and how we can write the three-dimensional. The same three-dimensional equation we can write in another form. So see, I h cross dou by dou t psi of, here you need to think r comma t equivalent to minus h cross square by 2m. Instead of the single only unidirectional x, you need to think about the all three direction, and then we can write in terms of del square Laplacian, including the Laplacian parameter. Del square psi of r comma t. This is what? This is three-dimensional Schrodinger equation. Right, this is three-dimensional Schrodinger equation. So if you include the force parameter, actually this is three-dimensional time dependent Schrodinger equation for a free particle, that is okay. Now here we can include the force parameter also. Actually inclusion of force. Actually classical energy expression means what? What is the classical energy expression that we know very well? E is equivalent to sum of both the kinetic and potential energy, no? P squared by 2m plus potential energy P. That is the total energy. This is a classical energy expression. If you want to tell the same expression in terms of the quantum mechanics, means we need to use this equation in three-dimensional direction. So here we have what we have, this side equal to this side, minus h cross square by 2m del square psi of r comma t, that is nothing, that is p square equivalent to the p square by 2m, and here we need to add that potential parameter with this, and finally that becomes how we can change it, minus plus I h cross dou by dou t psi of r comma t equivalent to minus h cross square by 2m del square plus potential term V of r comma t, that you can add it, right? It's a common term, you need to take psi of r comma t. So this is the total equation. I mean time, this is what? This is time dependent Schrodinger equation. Time dependent Schrodinger equation for a free particle of mass m moving in a potential V. Right. So this term, this equation number 10 is nothing. It is the time dependent Schrodinger equation for a free particle of mass m moving in a potential V of r comma t. So the quantity, actually you see this bracketed term, the quantity in the square bracket of this equation is the operator of the Hamiltonian of the system. So this is nothing, it is equivalent to the Hamiltonian. So the equation cannot be relativistically invariant as it contains first derivative in time and the second derivative in space coordinates. Okay. See students, this equation is a time dependent Schrodinger equation, and here you see this parameter is a kinetic energy parameter, and this parameter is a potential energy parameter, and this is nothing, total energy, right? So again we solve this equation. We can compare this equation with the classical expression also. So this is quantum mechanically the Schrodinger equation we are deriving like this. Okay students, thank you. So we will see the next video for the time independent Schrodinger equation. Thank you.